Alright everybody, first I want to start saying that thank you for all of you that came last Thursday night for the reposition class. I have seen the class and it looks good, but what I wanted to do was to shorten a little bit the beginning, because in any case this is just a bonus problem for the exams. I don't want you to go to a very large lecture. So the first thing I want to tell you about NMR is that it depends, or it is based on the nuclear spin. So you need to have a nuclear spin, so there's a NMR. Any charged particle that is rotating will generate a magnetic moment. So protons in the nucleus as well, they will generate a magnetic moment. That magnetic moment is defined by this equation, in which this y is what we call the gyromagnetic radius, and this I here is a quantum number that we call the nuclear spin angular momentum. But we can just call it the spin of the nucleus. So different nuclei will have different spins, and you will have this sheet that I'm gonna put in Allspace, so probably you also have it from the reposition class. And in this sheet you will probably see all the different nuclei that we can have, and it has their gyromagnetic ratios and the spins. So you can see basically all the elements, their spins and the gyromagnetic ratios. So depending on the charge of the nucleus and the amount of protons and amount of neutrons that it has, it will depend, will define the spin. For example, if I have even number of protons and even number of neutrons, then my spin will be 0. Likewise, if I have even number of protons and odd number of neutrons, then I can have spins that are either 1/2 or halves, like 1/2 or 3/2 or 7/2. Like for example, in the case of hydrogen 1, the spin will be 1/2, but for example for boron 11, the spin will be 3/2. So that kind of like tells you, that we can have half of integral numbers. When I mean integral numbers, I mean whole numbers, like 1, 2, and 3. Your number of protons is odd and the number of neutrons is even, you can have half numbers or integral numbers as well. But if your number of protons is odd and your number of neutrons is odd, you can have integral numbers, just 1, 2, and 3. So for example, carbon 12 has even number of protons and even number of neutrons, so carbon 12 doesn't have a spin. Actually, as you well know, carbon 12 doesn't present an NMR signal, and that's why proton NMR is in certain ways so powerful, because it doesn't have any interference or very few interference from carbon. On the other hand, hydrogen, fluorine 19, phosphorus 31, they all have spins of 1/2, and deuterium, for example, it will have spins of 1, and of course deuterium will have 1 proton and 1 neutron, so it will be odd, you have integral numbers. And I don't know, things like boron 11 will have spins of 3/2, things like cobalt 59 will have spins of 5/2. So in certain ways, if you have odd and odd, it's very easy to predict that you will have integral numbers, or if you have even, you have a spin of 0, but it's kind of like difficult to predict exactly what spin number you're going to have. So the easiest way is just to check it out into a table that will give you exactly the spin. So you look at the isotope, for example, boron 12 is 3, you can see it in the table, and boron 11 is 3/2. So if we go back to the nuclear moment, which is proportional to the gyromagnetic ratio and the spin, then one thing that you can notice is that the nuclear moment, that every single atom will have a different value for the nuclear moment. And the reason for that is that every single atom or nuclei have a unique gyromagnetic ratio. And that is what allows us to have a specific NMR, or we can set up a specific NMR experiment for different nuclei. For example, we can set a specific NMR experiment for just seeing at carbon-13, or we can set up a specific NMR experiment for just looking at hydrogen, because the nuclear magnetic moments of all these nuclei are different. And this is due to the combination of the gyromagnetic ratio and the spin. Well, the thing is that all these atoms that have a spin can have an NMR signal. So how the NMR works? Well, basically, you put your sample into a very strong magnetic field that here we're going to call B0. When you put your sample in that very strong magnetic field, what actually happens is that your spin, let's take a simple spin here, for example, the spin of hydrogen. Your spin is going to take different orientations in this field. And it can either orient in favor of the field, which will decrease its energy. If it is pointing toward the field, then its energy will be lower. Or it can be anti-parallel to the field, and that what it's going to do is that it's going to rise its energy. So spins that are parallel to the field, we're going to call them negative. And in this case, since it is hydrogen that has a spin of 1/2, then it can take these values minus 1/2. Or if it is anti-parallel to the field, then it will have positive values, and we'll call it 1/2. And this is just a convention. Scientists have decided that for NMR spectroscopy, if a nuclear spin is parallel to the magnetic field, then it will have negative numbers. That's it. So basically, you can see that your spin now you can say split in minus 1/2 or minus or positive 1/2. So this is basically a quantum number. So the projection of this number in the z-axis. It's a quantum number that we call ML. And ML can have values of I minus 1, simply until minus I. So in the case of a spin of 1/2, then the only ML quantum numbers that I can have are minus 1/2 and 1/2. And here you have them. So that is basically it. What we study in NMR spectroscopy is basically the transition of nuclei that are in the minus 1/2 spin to the nucleus that are in an excited state, in this case a 1/2 spin. So this is proton NMR spectroscopy. So basically you apply a radio frequency that is equal to that energy gap, and then you make that proton or that nuclei that have an antiparallel spin parallel spin, you apply a radio frequency, and then you flip that that nuclear spin. It can be the NMR spectroscopy can be understood in terms of this. The thing about NMR spectroscopy, and as you can see here, is that it depends on the population of spins in the lower level toward the population of spins in the upper level. So, and this is actually the problem with NMR spectroscopy. Because when you put a molecule, and let's keep talking about hydrogen because it's a very simple system. If I have hydrogen and I put just simple hydrogen atoms, let's say in the gas phase, into an NMR spectrometer, then there will be a field, B0, and then I will have many NMR nuclei, many proton nuclei that are going to orient in favor of the field, but I have also a lot of nuclei that are going to orient anti-parallel to the field. And this energy gap is about 10 to the minus 25 joules. So this amount is extremely small for a field of about 8 Tesla, which is, you know, not completely wrong for an NMR spectrometer. Then a field that strong will create energy level separation with that energy gap. And if we use Boltzmann equation to calculate the population of the two states, what we will find out is that, for example, if we have 100,000 molecules or 100,000 hydrogen atoms there, basically 50,000 atoms will be in the excited state and 50,000 001 atoms will be in the ground state. And basically what you are exciting is this very small population of atoms that are in the ground state into the excited state. So that is why NMR spectroscopy is a very insensitive technique. And actually, to do an NMR experiment, you require a lot of sample. This can be circumvented by increasing the magnetic field. If you increase the magnetic field, then you increase the distance between these two levels. And if you increase the distance between these two levels, then you increase the population of the lower level. But if the distance is small, thermal population will allow the upper level or the excited state to be almost equally populated as well. Well, this is for a standard nucleus with spin of 1/2. But what happens if you have a nucleus like, for example, boron 11? So in the case of boron 11, you have a spin, a nuclear spin of 3/2. And that nuclear spin of 3/2, when you put it in a magnetic field, it will get values of ml that are, if you remember, it will have values of I minus 1, like that until minus I. So basically, the values of ml that are possible are 3/2. 3/2 minus 1 is 1/2. Minus 1 is minus 1/2, and minus 3/2 up to minus I. So what that means is that when I put this boron 11 nuclei, an example of boron 11 nuclei in the NMR, then their energy levels are going to split to minus 3/2, minus 1/2, 1/2, and 3/2. And there you go. So nucleus or nuclei that have spins that are higher than 1/2 are called, let me write it here, nuclear. Okay. Are called quadrupolar. So boron is a quadrupolar molecule, and it will have this kind of like splitting when it is in a strong magnetic field. So the selection rules, as you remember for hydrogen, boron, hydrogen, you can have transitions from -1/2 to 1/2. The selection rule for transitions in NMR, it is that ML can be ±1. So in this case, ML is 1, so this is an allowed transition. So in this case, I can have transitions from here to here, from here to here, and from here to here, because that would make ML ±1, and if I take the NMR of gas phase boron atoms, how many peaks would I expect to see? Well, I asked this in class, and some people said 3, and some people said 1. Well, although I have transitions that corresponds to 3 transitions, those 3 transitions have exactly the same delta E. So although my signal will be will be due to 3 different transitions, those 3 different transitions will have the same energy. So in an NMR spectrum of boron 11, atoms flying, not boron 11 molecules with something else, boron 11 atoms that is not coupled to anything else, then I will have a single lone signal. So that's basically it. So now, if you have all this information, then you can construct NMR spectrum of any molecule. So let's do an example. So let's say that we have CH4, standard organic compound. What would be the NMR of CH4? Why? I have 4 hydrogens. But they are all equivalent, right? So I will have just 1 peak for hydrogen. How many peaks will I have for BH4? First of all,
what range are we in? Are we looking at the boron or are we looking at the hydrogen?
Excellent question.
Okay.
Drop an NMR. Well, at least 1. At least 1. Right? The problem is, in this case, different than carbon. Carbon 12 doesn't have a nuclear spin. But in the case of boron, boron does have a nuclear spin. Where's the nuclear spin of boron?
Depends on the isotope.
Boron 3, boron 11. 3 halves, right? So, and now it's all the sigma mi, which is the splitting. The splitting of any atom is going to be equal to 2I n plus 1. I'm just going to do the demonstration. 2 times the spin of the species that is coupling, which is boron 3 half. How many boron 3 half there are? 1 plus 1, so that means 3 plus 1 means 4. The hydrogens are all the same, so my proton NMR spectrum is going to be a beautiful quartet, and the intensity of those bands will be exactly the same. If you have to report the chemical shift, it will be exactly between those two. Are you confused? What if I enrich my methane and all my methane is now carbon 13? What will be my proton sigma, my proton NMR? A doublet. In an enriched sample of carbon 13, methane will be a doublet. And in a real sample of of methane that has what is the abundance of carbon 13? Is it here?
1.1%.
1.1%, right? So in a real sample of methane, you probably will never notice it, but you will have your singlet and here at 1% you will have something like this. Those are what we call the satellite bands, and they're due to the carbon 13 that is present in the sample. Probably you will never see it because it's below 1%, but it's there.
So this one is for the carbon and this one is for the hydrogen?
No, this is for standard CH4.
Oh.
This is for enriched CH4 with carbon 13. The thing is that normal CH4 will have 99% of these and 1%. Are you with me? Because now, if yes.
So that means that for 13 CH4, would you get a? Oh wait, no, you wouldn't get a small spike from C12.
I'm sorry.
Because so for the normal CH4, you showed us that you get a small 13 C spike, right?
Mm-hmm.
So I was going to say that does that mean that you will does that mean that you will see a small 12 C spike, but you won't because there's
No, exactly. And this is 100%. I'm saying enriched 100% C13. Okay, now what happens if I ask you to do the boron 3 half NMR? Boron 3 half NMR. What's going to happen? How many different borons do I have? Only one. But what's going to happen to that boron? Is it as isolated? It is not isolated. It is what? What does it feel? The field from the hydrogens. There's a magnetic field from the NMR detector, but then the hydrogens around this boron are coupling parallel or anti-parallel to that magnetic field. So that's going to change the energy of the transition of boron, depending of the orientation of those hydrogens. So how many orientations those hydrogens are going to have? Well, I can have them all parallel. So they can have all 1/2 spins, right? The sigma mi there will be 2. And how many ways I have to organize this? How many permutations can I have?
One.
One. Of course, a population will have that, but then a population will always also have most of them facing the magnetic field, but one facing the other direction. The sigma mi there will be 1. And how many ways? One way. How many ways, how many permutations I have for that?
4.
Let me see, 1, 2, 3, yes, 4 ways. Do you see it? I can have that. I can have, I'm going to write it below, but then I'm going to erase it. I can have that. I can have 1/2, 1/2, minus 1/2, 1/2. I can have 1/2, minus 1/2, 1/2, 1/2. And I can have minus 1/2, 1/2, 1/2, 1/2. I have 4 different ways in which I can order that. Right? 4 different combinations. Alright. Another one. I can have how many ways I can order that? I can rearrange that. 6 ways. Do I need to do it or can you see it?
Yeah.
Then the other 2 possibilities are very straightforward. So we can have minus 1/2, minus 1/2, minus 1/2, and 1/2 positive. This will be minus 1, and there will be 4 ways. And then we can have minus 1/2, minus 1/2, minus 1/2, minus 1/2. This will be minus 2, and there will be
1.
very good. So how many boron signals are going to have? 5. 1, 2, 3, 4, 5. Due to the different orientations that my spins can have. I have 5 different orientations. If you don't believe me, then you can go to the splitting formula. 2in plus 1, 2 times 1/2, because now the things that split are the hydrogen atoms, times 4 plus 1, that makes 4 plus 1 equal to 5. The splitting formula tells you how many lines you're going to have, but it doesn't tell you what will be the abundance. So in this case,
There's a 1, 4, 6, 4, 1 pattern.
yes, my splitting will be 1, 4, 6, 4. Of course, you didn't need to do this, because I can tell you right now that every time that nuclei with spin of 1/2 are splitting, then you can use something that you used in organic chemistry a lot, that is called the Pascal triangle. So, if and only if the nucleus or the nuclei that are splitting have a spin of 1/2, then you can use the Pascal triangle to determine the split. Are you with me? Can we make it harder?
Let's.
What is the boron? No. Let's make the molecule. And actually, I'm gonna put here an alkene just for the sake of not having any splitting. So actually, I'm just gonna put here arginines, just not to complicate too much the molecule. Our groups, they are quaternary carbons. They are all carbon 12. They don't couple with anything. So yes.
So in the previous example, you were doing the sigma NMR. What's that? Like your 2, 1, 2.
That's the total spin. You don't. That's the total spin. So if I have 1/2 plus 1/2 plus 1/2 plus 1/2, the sigma mi is 2.
And is that the same as the 2 ion plus 1?
No,
That is also.
no. That the 2in plus 1 is a split. So it's basically the different ways I can organize this. I can organize the sigma mi's to give the different permutations.
That also stands for the energy levels.
The sigma mi.
I mean, it has the.
It basically is basically related to the number of energy levels that there are. Okay. So what about that? If I ask you to do the boron, well, what do you want to do, the hydrogen or the boron?
Both.
Both. What do you want to do first?
Boron.
Boron. You know how to choose your balance. Boron. So boron is coupled to what? To hydrogens. And we are assuming that the borons cannot couple to each other, which they could. But let's assume that they can to make it simple. So how many different borons there are? One. So there are 2 borons, but they are equivalent, right? They're equivalent borons. How many hydrogens I have? How many different kinds of hydrogens I have? One. Right? So the boron, we have NMR will be what? Well, the signal of boron, which is just one boron, and it would be splitted by hydrogen. So
Do we ignore the hydrogens that would be with the R group because
These R groups are quaternary carbons. Quaternary carbons.
okay.
Yeah, I said that they were quaternary carbons specifically so you don't have problems there. So, I have two hydrogens. I fill the field for those two hydrogens, and my splitting is going to be what? 2 times 1/2 times 2 plus 1, which is equal to 3.
Yes.
But since what is splitting me is a molecule, an atom with a spin of 1/2, I can use Pascal triangle, and then my boron NMR signal right?
Yes.
Are you with me?
Yes.
Because you're not gonna like the proton signal.
They're bonus, right?
Wait, why is the I?
What?
Why is the I transfer the I is true?
The I is of the splitting, so is of the atom that is splitting. So it is hydrogen. So that's the splitting formula. So it's for the atom that is split. All right. So boron. So hydrogen NMR. What is my problem now? My problem now is that I have a proton NMR, and now I have two boron atoms that are going to split the signal of those protons, right? What happened now is that I would love to tell you that you can use the Pascal triangle, but you can't. Why?
The spin is 3/2.
Because the spin is 3/2 and you cannot use Pascal triangle for anything that is larger than 1/2. So you can use the splitting formula if you want.
Is there another triangle?
There's no other triangle.
Is there a square?
There's no square.
Brothers.
You can use the splitting formula if you want to get scared at the beginning. So that would be what?
4.
At least you know that your splitting will be 7. Is that the hard part? Just look.
That was the lowest point.
You know, it's that sign. The order would just have a name.
This is a Thursday night syndrome. Alright, so there are different ways of doing this. So basically you have two boron atoms. The first case that you can have is that you can have the two spins having both oriented towards the field with 3 halves, right? The sigma mi is going to be what? 3? So how many ways I have that my sigma mi is 3? 1 way. The other case that you can have is that you can have one still at 3/2, so the other 1/2. Then your sigma mi is going to be 2. And how many ways? Yes, 2 ways. But of course, you can keep going, and the other thing that you can have is 1/2 and 1/2. You have to keep your sigma mi going from top to bottom, right? So then what? How many ways that your sigma mi is 1? No, There's two.
Because there are three atoms.
There are 3 ways, right? 3 ways that the sigma mi is 1 because it can be this, but it can also be 3/2 minus 1/2, and of course the inverse of this. So that makes it 3 ways. Are you with me?
Yes.
So then the rest is just keep going. So minus 3/2 and 3/2 will give you a sigma mi of 0, right? How many ways?
4 ways.
4 ways.
And then can we assume it's symmetrical and then it's going to repeat now, or can we not do that?
It's gonna repeat.
So there is a triangle.
Yeah, but if you do it with something of 5/2, you will remember that it will not give you the same thing. But with 3/2, okay, and if there are 2, all right, you ruined it. Anyway, so in order to have sigma mi of -1, -2, and -3, then my counting will be -1/2, -1/2, and of course there's 3 ways of doing this as well, because you can have the -3/2, 1/2, and the inverse, and then for -2, I can have -3/2, 1/2, and there are 2 ways of doing that. And for the -3, it has to be -3/2, -3/2. So in any case, there's just one way of doing that. So your proton NMR for this system is gonna be one, two, three, four, three, two, one.
Hey, I honestly don't get why, like, let's just say 1/2 and 1/2. How do you get to 3 ways again? Like, you're talking about some kind of inverse,
3
but I
ways?
kind of missed the boat right there.
Okay, you can have these 2 spins. There's only one way of having these 2 spins. If you invert them, it's exactly the same. But these 2, you can have 3/2, 1/2, or you can have -1/2, 3/2. That means that either this is 3/2 and this is -1/2, or this is 3/2 and this is -1/2. They're different. So you have 2 ways in which you can do this. These 2 ways, and this that is the same. Then you have 3 ways. 3 ways in which the sum of MIs -1/2 -1/2 is 1, 3/2 -1/2 is 1,
Oh,
-1/2 plus 3/1 is 1.
okay.
3 ways in which your combinations can be used.
Okay.
My question, so, I think this is the hydrogen is basically the bromine, so why we have the 1/2, but no, why we have the 1/2 for the
Because the MI numbers can be I -1, I -2, 2 minus I. So that means that my MIs are 3/2 minus 1/2 minus 1/2 and minus 3/2. Right?
So we can just take any number from
Questions? More questions? Good? Really?
I minus 1, I minus 2. Does it go to I minus 3?
It goes as much as you need, so it goes to minus I. So if my I is 3, for example, it will go from 3 to minus 3 in intervals of 1. 3, 2, 1, 0, minus 1, minus 2.
So what's the change in variables?
The change in MI,
I'm sorry, the sigma. What does it represent?
it represents the number of energy levels. So this represents that you can have 3, that you can have 2 spins oriented in the same direction. So it represents the total momentum of the dynamo.
And each momentum is a different angle.
Each momentum is a different energy because when you have 2 3/2 oriented with the magnetic field, the total magnetic field that fill the hydrogens is stronger because you have the sum of the 2 borons plus the magnetic field of the instrument. When you have that magnetic field reduced to 1/2, then the magnetic field that the hydrogens feel is strong, but not as strong as this. So it is 2. It is strong, but not as strong. And then you get to 0, in which they don't feel any field, just the field of the instrument. And then they start feeling less field because then now the spins are pointing the other direction. So it represents the total magnetic moment contribution from the spins.
So when we are essentially like plotting the spin, like we have to basically draw the spinning on. So are we, so on the axis, are we basically putting down how many ways that was like what's on the axis?
In the axis.
Yeah, on the
I'm just saying the contribution. So the signal, it would be 4 times this, 4 times this. This is 1. This would be twice as big. This would be 3 times as big. It would be 4 times as big.
So each time, so basically each of the contributions is the energy level or how many ways you can have.
How many ways you can have? Because basically what you're counting is the number of microstates in which you can have. So the number of ways that this can be organized. So there's only way that you can have 3/2 spins, but there are 4 ways in which you can have 0 spins. So since this is random by probability, you will have 4 more times 0.
And for the energy levels here, is that true that the energy gap between the continuous energy levels are the same, right? For example, from the 3 to 2 and from the
No.
2 to the same.
No. The energy levels are changing. That's why we have the splitting. Each one of these lines have a different energy.
Yes, but the gap.
The gap is changing.
The gap is also changing.
If the gap doesn't change, the energy doesn't change.
I mean, the gap can be constant, and the energy is still,
No.
I mean, 4, 3, 2,
The
1.
gap is constant for 1 atom.
Uh-huh.
But here we have 5 different combinations. So you could say that an atom that have this configuration and a molecule that have this configuration is different than a molecule that have minus one half configuration.
Yeah.
They are magnetically, they are different molecules. So for this combination, the gap is the same, but it's different than the gap from this combination, or for any of these combinations.
All right.
Questions? Yes.
So how would our analysis of this changed if it had been diborane instead of with the carbons? Like,
With hydrogen,
yeah,
with other hydrogen.
with other hydrogens. I guess my main question is then do you just like use more hydrogens for that equation to get the splitting and then use the same triangle? And then does it change anything with the protein?
But you have to remember that the splitting formula works for the same kind of hydrogen. But is that kind of hydrogen the same kind of hydrogen? So then you will have a second splitting that you will have to calculate. Right?
Like two separate problems.
You have two separate problems. You first solve one and then you solve the other. That's basically the way it works. Yeah, I didn't want to go that way because the spectrum will be a mess if you start splitting that. But I mean that is basically the way you solve one and then you solve the other. Other questions?
So when we are doing the listing of the spin numbers, essentially, so first of all we pick the atom that's splitting one bigger.
Yes.
And we also like they're like for example here we have two. Let's say we had like 3 hydrogens in between which are going to
If we have
if you have like the 2 bonds connected to 3 hydrogens, just let's just say, then you would have 3 of those.
if you have 3 bonds with 2 hydrogens,
No, so you have the 2 bonds.
the 2 bonds.
And in between the 2 hydrogens you have 1 more hydrogen.
One more hydrogen.
Yeah, so you would have 3 of those.
Can I have others?
So when you're doing the listing, you will have 3 rows and then you do it. Right.
If I have an extra hydrogen there, what spectrum we are? Boron or hydrogen?
The board. I mean, basically what we just did.
The same that we just did. Are the 3 hydrogens equivalent or not? Let's suppose that the 3 hydrogens are equivalent, right? They're kind of like forming a triangle. Let's assume that they're equivalent. So if the 3 hydrogens are equivalent, how the spectrum is going to change?
You have 2 rows.
Huh?
So you have 2
Huh?
Two more splits. The number switch from 2 to 3.
How the proton NMR spectrum is going to change if I have one more hydrogen? Let's do the splitting formula again. 2 times what? 3 halves times what? Times 2 plus 1. How is my proton NMR going to change? In no way.
What about the?
What is going to change? What it does going to change is what?
The borrowing amount.
Nothing.
No.
No, in the proton NMR, nothing is going to change.
Yeah, but-
Where I going to have a change?
For the borrowing amount.
In the boron NMR. In the boron NMR, then I'm going to have what?
Yes.
I will have a 1, 3, 3. Yes?
Does the magnitude of the heights change as a function of the number of protons that you have?
Here?
Yeah. Or
But-
does it just matter that the relationship?
It doesn't really matter.
Okay.
Well,
I don't know.
if I have, you're talking about if I have other protons. If I have 2 other protons that have other splitting around here, I don't know, then this will be 3 times as this. Is that what you mean?
Yeah.
It will be more intense because I have more protons, the intensity. But the splitting
Is the same.
will be exactly the same.
So if we have the one extra hydrogen between the boron, so what does the formula mean? It will be 2 times still 1/2.
I'm sorry.
Oh,
What will change?
So the formula.
The formula? The formula will just change here. Instead of 2, I have 3. So that would be 4. And how many I have in my Pascal triangle here?
4.
131.